Hello and welcome to today's webinar with 42Crunch, a review of the API security breaches from the first half of the year. Just before we kick off, a little introduction to our speakers. First up, we have Anthony Lonergan. Anthony, who has the dual responsibility of editing our fortnightly API Security.io newsletter. If you're not already familiar with the newsletter, I'd highly recommend you sign yourself up after the webinar. Anthony also leads our developer relations, and now that we've hit over 1.3 million users, needless to say, he's a busy man. And also joining Anthony today, we have Heshaam Attar, who will assist with the live Q&A at the end of the webinar. Heshaam is a solutions engineer who works with many of the world's leading enterprises as they seek to solve their API security challenges. Today's speakers have a lot of experience working with customers and partners to help them with their API security requirements in the field, and are very well qualified to speak on this topic. It's an ever popular one, and never ceases to draw a large crowd and generate a lot of questions. So we do hope you'll be able to submit your questions to us, and we'll get to those at the end of the session.
Okay, so in this session, we're going to take a look at some of the API security incidents that were in the news this year. Now, there's many cases that we could choose from. We're seeing a lot more companies getting caught out by API vulnerabilities already in the first half of this year. But we've narrowed down to a few specific cases that we think can help to learn the most about how APIs are regularly being attacked and compromised. So in other words, what can we learn from these cases to help make our own API development more secure? So we'll divide this webinar into three sections. First, for context, we're going to quickly review the specific industry cases that we want to focus on in terms of who was the target, what was the vulnerability, and what damage was done. And then second, we're going to delve into the vulnerable APIs for each case. We're going to examine the API behavior, we'll review the company's API documentation, and then we'll try to understand the origin of some of these problems from the API development perspective. And then finally, I'm going to demonstrate some API development practices that we support at 42Crunch that would have helped teams to catch and prevent these vulnerabilities and secure the APIs. All right, so let's start with a quick overview of the incidents. And first up is this report of an exploited vulnerability in the Trello REST API. Now, if you're not familiar, Trello is an online project management tool. It's often used by teams to manage project data and collaborate on project tasks. So the application supports a lot of interaction between members and data sharing, and that's facilitated by APIs. Now, according to the report, a hacker scraped over 15 million member profiles from Trello and then was able to link each member's profile with their registered email address, which was supposed to be private. And this was done through Trello's API. Now, Trello insists that, strictly speaking, this wasn't a breach since the profile data that the hacker got from their API was public data anyway. And also the email addresses that were used by the hacker didn't come from the Trello system, and that also appears to be true. But a key vulnerability here was the ability to link these two pieces of information together, a member's profile data on Trello with their private email address. And that link was possible, it was actually verified through the Trello API. Now, the extent of the problem and the fact that so many millions of users were affected, this was made worse by a lack of API authentication and a lack of rate limiting on the API. But certainly more companies are falling victim to these types of mass data scraping attacks through APIs. So this is one case we really want to delve into a little bit more. Now, the second report involves vulnerabilities in F5's Big IP Next platform. This is it's a relatively new flagship product from F5. It's used for centralized management of network and application infrastructure. And if a hacker finds vulnerabilities in a management platform like this one, they can use it as a launchpad to gain privileged access deep into customer systems. Now, the discovery here was by a firm called Eclipsium, and they found 5 different vulnerabilities in the same F5 device, including SQL injection, weak password hashing, and SSRF, or server-side request forgery. Now, this case, I think, is a bit of an eye-opener since the company that was vulnerable, F5, they actually specialize in application security. So to find these types of well-known vulnerabilities in the APIs of such a critical F5 product, I think it's really worth us taking a deeper look to understand what's going on with the APIs and how can you avoid similar types of incidents. And then the third case we're going to look at is Spoutable, which is I guess it's a social media company, similar in concept at least to Twitter, or X as it's now called. Now, there's an excellent write-up on this case by Troy Hunt, which I definitely recommend. It takes you through his discovery process step by step, and then explains the different vulnerabilities found with Spoutable's API. Now, our focus with this case is specifically on the risk from excessive data exposure in the API response, because even if you do all of the work of strengthening and protecting your APIs from outside attacks, your APIs can still leak private information in a very damaging way on the outbound or the response side. Okay, so with these three cases then, we can cover API vulnerabilities across the full transaction to include both API breaches on the request side and data leaks on the response side. So those are the cases we want to focus on. Next, let's take a technical look at the API vulnerabilities for each of these incidents. Okay, so first up is Trello, and this API is used to look up the profile data of any Trello member using either their Trello ID or their Trello username. So for example, I can use my own username to get back my member data. So we see the API response with all my profile data, and because this is my account, so the API response includes my email address. But if I use the same API to look up another Trello member, we see similar data is returned by the API, but notice this time Trello redacts the email address in the API response. And this is a central issue because the email address of other members is supposed to be private. So this is the API working as it's supposed to. Now let's turn to the Trello API documentation. And here it describes the API we were just looking at to get a Trello member using either their Trello ID or their username. Now further down, there's another description of how to update a member. And here Trello provides a specific requirement for the format of the Trello ID. So it says it must be a 24-character hexadecimal string. And here's an example. And then likewise for the username. Now they don't provide a pattern here, but there's a description of the requirement. It says it must be at least 3 characters long. Now I've tested this and the longest length allowed is 100 characters. So we're talking 3 to 100 characters long and using only lowercase letters, numbers, and underscores. So Trello developers have set very specific requirements on these API inputs for either the ID or the username, and then they enforce those requirements. So for example, if I try to update my Trello username, and if I break the rules by using, let's say, less than 3 characters, or using uppercase letters instead of lowercase, you can see the API enforces the rules and rejects the input. And that's what the 400 response from the API indicates here. So the API is responding that it won't accept this bad input. And then likewise, if I try to change my username to make it an email address, which again is not a valid username because it uses characters like @ or ., it's the same response. 400, bad input, not accepted. And now let's try the exact same input, but this time on the get operation. Now remember, based on the Trello docs, it should accept either an ID or a username as input, and an email address, again, is neither of those. So it should be rejected by the API as bad input. But this time we see the API returns 404 not found instead of 400. Now we'll touch on this a bit when we talk about API security testing, but this difference between 400 and 404 is really important, and it's what hackers are often looking for in your APIs. Because what 404 means here is that not only did the API accept bad input, it even used it to search the database. All right, so we found a vulnerability in the API. Now can we exploit it? Well, what if I can guess an email address that is registered for a Trello member? So now we see that if a Trello member exists for this email address, we are getting the profile data back, even though the API was documented to accept either a username or an ID, not an email address. So here the API is effectively verifying, yes, the owner of that email address has a Trello account, and here's their member data. And this is essentially what the hacker did here. He just, he did it in bulk. So he could take a list of email addresses, and then using this API, he could verify if they were registered on Trello. And if they were, he would get back their Trello profile data, which was linked to a private email address that he used. So it didn't matter anymore that Trello had redacted the email address in the response, because the hacker would still know the email address for that member. So that's the vulnerability that was exploited in this case. Next, we're going to consider how the vulnerability might have arose in the API in the first place. So this is the Trello Open API file. It's also public and it's available online. I've opened this up in the 42Crunch Open API editor because it's a pretty big file. It has, I think, over 16,000 lines. And the Open API editor allows me to quickly navigate to where we want to focus on in the Open API file. So let's look at the API endpoint in question again, and it's the get member operation. So now we're looking from a developer's perspective at the API. So this is the endpoint. We see it accepts an input parameter called ID. And again, the description tells us that this input can be either the Trello ID or username. Now this part is really key. So here's the schema. And this is where the API developers set out the precise data requirements for this API at runtime. And it's telling us that the ID can be one of either the Trello ID, and let's first take a look at that. So this is the definition for the Trello ID, and here's that important pattern. So this corresponds to what we saw earlier on the website. And the API developers have correctly documented here that the requirement for Trello ID is that it must be a 24-character hexadecimal string. So that's quite precise, and that's correct. But now let's look at the other definition, which would be for the username input. And this just says that the input must be a string. There's no other rules about, being between 3 and 100 characters long or using lowercase letters and underscores. It just needs to be a string. Now, that could be anything, right? It could be a Trello username, but it could also be an email address or a SQL injection pattern or a path traversal pattern. This could be any input that a hacker wants to use to probe and attack your API. So that's the underlying mistake in the API development that created this vulnerability. The input allowed for this API, it's not precisely defined and enforced by the development team. So now let's look at the next case. This time it's the F5 Big IP Next device. Now the exploit here is different to the Trello case that we just looked at, but watch how similar the underlying API vulnerability is. So I mentioned earlier there was 5 different vulnerabilities found in this F5 device, but we want to focus on the SQL injection vulnerability because for years this SQL injection, it keeps catching out developers and exposing companies to breaches. And in this particular case, it was probably the most severe of the 5 issues because it allowed unauthenticated users to steal admin credentials from F5's SQL database. So this is the SQL injection pattern that was used. It's a little bit difficult to see it here. Okay, so you can see it's a long string. It has over 200 characters. So why was this input, this strange long string of characters, why was this accepted as input by the API? So again, we can do the same analysis as we did before. Here's the online documentation again for this API. This was the API operation hacked, and this was the field that was vulnerable to SQL injection. So the documentation describes this field as a non-empty string. And then if we move into F5's Open API file, we see this again was the endpoint that was hacked. This is the schema for the API's input that describes the requirements for the API's data. This is the vulnerable field, And here again, we see the only requirement for the input is that it must be a string with a minimum length of 1. So there's no other constraints or limits on what the input can be. And so that answers the question of why that long SQL injection pattern was allowed. It was allowed because it matches what's required by the API definition for this input, which is a string that's longer than 1 character. That's it. So that input requirement is so loosely defined, it leaves a very wide scope for hackers to try different types of malformed data for this provider name property. That then opened the door for someone to find a SQL injection pattern that worked against this API. So for both the Trello and the F5 incidents, the exploits were different, but we can trace the API vulnerabilities back to the same underlying cause. The developers haven't properly defined and enforced constraints on the API's input, and so that creates the vulnerability for someone to exploit. Now, for the third incident that we want to look at, which is the Spoutable case, I couldn't find any public documentation for their API. But based on a report of the vulnerability, this is at least in part what the API data look like. And here the issue is mainly with the response data that's returned by the API. So many of these properties would be considered sensitive or private, so these shouldn't be exposed by the API. We see information coming back like the IP address, password, secret, backup codes. So just as we saw with the API request, if the API response data is also loosely defined or it's not defined at all, then it's easy to see how something like this gets missed by the development team and the testing team. Because if teams don't know what data the API should return, if we don't document that, for example, then developers won't know what behavior to code in the API, and testers won't know what behavior to test for in the API. So here's an example of what that should look like. So again, we're using OpenAPI to define the response data for this Spoutable API. And this indicates that only these particular properties are expected in the response and no additional properties. So this is something that could be given to a testing team to test if they can make the API behave unexpected and return data that it shouldn't. So for each of the cases that we've looked at, for Trello, F5, and Spoutable, the security incidents were different in all of these cases, but they all have the same underlying vulnerability. And that's that the API accepts bad data in the request or it's leaking unauthorized data in the response. And then we've traced those vulnerabilities back to the API development and particularly the OpenAPI file. So let's clarify exactly what OpenAPI has to do with API security. So this is an example, and it's often referred to as either an API definition or an OpenAPI contract. But essentially, it represents the software requirements for an API. So you can see it sets out what are the endpoints and the resources exposed by the API. It sets the read and write operations that the API supports, what security tokens are required, what input or output properties are allowed by the API, and then precise limits and constraints on those properties. So if an OpenAPI contract is well written, it makes clear what data the API allows or requires at runtime. And then conversely, if the OpenAPI contract is poorly written with mistakes or it's too loosely defined, that creates ambiguity for developers and testers, and it may end up allowing the wrong sort of data to pass through the API. And so that's the root of the problem across all of these cases that we're looking at. So now let's look at some API development practices that can help to build APIs that avoid these vulnerabilities in the first place. Okay, so we want to start by making sure that the API data is well defined and the requirements are clear. So let's look again at the Trello OpenAPI file. Now there's thousands of lines in this OpenAPI contract. So how would a team find where the API requirements are missing or incomplete? So we use API audit to check an OpenAPI file and find if it contains mistakes or if it's incomplete in a way that can introduce a vulnerability. So for example, if we run API audit on the Trello OpenAPI file, what would it find? So the audit is now checking the file against the Open API standard, and then it's cross-referencing for security vulnerabilities. So here the audit report indicates that this input property is not constrained by a data pattern. So remember, this was the issue with Trello's username property, which it only required the input to be a string, and so the API accepted email addresses in the input. So just by using API audit, it draws attention to this potential vulnerability in the API. Okay, so now the team knows that this input is missing precise requirements. So how do we make it easy for developers to add that information? One way is to use a data dictionary, which you can use to store precise rules and requirements for common properties that are used in your APIs. So here's an example that I added for a username property. And you see it's got those constraints that Trello requires, that 3 to 100 characters long, lowercase letters, numbers, and underscores only. So then to use this anywhere in the Open API contract, I just need to specify that the property format here is username. And now the tool automatically completes the requirement for username. So now it's clear what Trello's API should accept for the username input. But if I search for username in the rest of this Open API file, we can see there's many other places where the input is vulnerable because, again, it's so loosely defined. So we'll want to update these properties as well. Now I'm going to use a bit of a shortcut just to add our format specifier throughout this document wherever it's needed for username. And then in one go, I can update every instance of username in the Open API contract to complete the requirement. So now for all of these input fields, wherever we're using username, we're reducing the opportunity for malicious input to enter our API because we're being very precise about what data is allowed. Okay, so let's do the same for the F5 vulnerability. Now remember here, it was the provider name field that had a very vague requirement for the input. So it just needed to be a string that was longer than 1 character. And that exposed the API to SQL injection. So again, running API audit, we see it again draws attention to this vulnerable input property, and it's highlighting that this is too vague. So it's missing both a constraining pattern and there's no limit on the max length of the input here. Now this is interesting actually because later in the file I noticed there's another instance of provider name, and here it does include a maximum length of 64 characters. And if we remember, the SQL injection pattern that was used against the F5 device was much longer than 64 characters. So just by adding one extra constraint on the API input property so that it's using no more than 64 characters, that's the maximum allowed, suddenly that SQL injection pattern doesn't work against F5's API. So again, the key point is that the more specific your Open API contract, the less room a hacker has to attack your API. All right, so now we've improved the Open API contract, but just documenting rules isn't enough. We need to make sure that those rules are part of the running API. So for example, does the API now limit the input to a maximum of 64 characters for this provider name, or does it still allow a very long SQL injection pattern? To test the API, we use a tool called API Conformance Scan. So it reads the Open API contract, and then it learns the rules to understand what the API should allow, and then it breaks each rule to see how the API behaves. So for example, if a hacker sends bad input to the API that doesn't match the Open API contract, does the API reject the bad input, or does it accept it and then expose the vulnerability? So now for this demonstration, I've created a simulation of the F5 API, which is running on my local machine, along with an Open API contract. And from here, we can open the test interface for API Conformance Scan, and then I'm going to start to run the conformance test. So now API Scan is sending test requests to the API that purposely breaks all of the rules in the Open API file one by one. And then depending on how the API responds, we'll know if it has vulnerabilities. So this is the API scan report. And this is the list of all of the issues found where the API is not behaving according to the Open API contract. And if we search, for example, for the tests related to input length, we can see that the API is failing this test. Because here for the provider name property, the API should reject input that's longer than 64 characters, but the test shows that the API allows it. So we can see that in the report summary. It says the expected API response was 400, which would indicate the API rejected the bad data. But the actual response from the API was 404, indicating the API accepted the data and tried to use it. And that's similar to what we saw in the Trello example earlier. So a hacker is looking for those 404 responses from your APIs, and so API scan looks for them as well. So basically, this API is still vulnerable to that long SQL injection pattern that we saw earlier, not to mention many other attack patterns that a hacker could try on this API. And so again, this is something that a testing team could find using the Open API contract. So the contract states this is how the API is supposed to behave, but the test shows different. And that would highlight to this team something that needs to be fixed, ideally before the API goes into production. Now, for each of the cases that we've looked at, for Trello, F5, and Spoutable, the vulnerable APIs were found in production. So how could a team protect those vulnerabilities from being exploited when they're already in production, at least until the developers get around to fixing the bugs in the API code? Well, we know that the Open API contract contains all of the rules for what's allowed or required in the API request and response. So we can leverage the Open API contract and we can use it to enforce the rules on behalf of the API. So for this runtime enforcement, we use the API firewall. And the firewall is configured directly by the Open API contract. So it's deployed along with your API, and it checks all of the traffic to and from the API to check if the data conforms to the Open API contract. So for example, in the Trello case, the API firewall is configured with the Trello's Open API contract, which we've already improved with a more precise input definition. And so if any request comes in that isn't strictly a Trello ID or username, then it's the API firewall that rejects the request and protects the API from misuse. And then likewise for, let's say, the Spoutable case, the API firewall is configured again with the Open API contract for Spoutable, and that precisely defines the only properties the API should return. And then if the API accidentally leaks excessive data that isn't defined in the Open API contract, the API firewall blocks that response and protects the API from leaking private information. So I've already set up both of these scenarios. So I have a simulation of the Trello and the Spoutable APIs that are running locally on my machine. And then I've imported Open API contracts into the 42Crunch API security platform. And that's where I can convert both of these into configuration files for an API firewall instance. And then I've deployed an API firewall in front of each of the local APIs, one for Trello and one for Spoutable. Okay, so the API firewall is enforcing the Open API contract for each of those APIs. All right, let's test this, and we can try, first of all, the Trello example. So I'm going to start by sending a request to the API directly, so not going through the API firewall. So we can see it accepts the ID, the Trello ID, and it accepts the username. But it still incorrectly accepts the email address as input when it shouldn't. So now let's send the same request through the API firewall, which is now enforcing the Open API contract. So these first two requests are still valid using the ID and username, so they're allowed. But the email address isn't the expected pattern. So that's rejected as bad input by the API firewall. And then likewise, let's try the Spoutable API. So again, we'll first try sending a request to the API directly, just to confirm the behavior. So we see it's returning that excessive data that's not defined in the Open API contract, which was the vulnerability, the original vulnerability we saw with this API. And now if we send the same request, but this time we go through the API firewall for Spoutable, which checks both the request and the response. It finds that the response has excessive data that's not defined in the Open API file, and so it protects the API from leaking that data. Okay, so these are some of the ways of developing APIs to prevent breaches and vulnerabilities. And if you're following the API security.io newsletter, you'll see every week there's new reports of similar API vulnerabilities that can be traced back to a lack of proper API data validation. So hopefully some of the practices that we've gone through here will help your own API team avoid these same vulnerabilities.
Great. Thanks, guys. Hopefully, we've got a few questions here that we'll be able to go through with folks. They're coming in thick and fast. So, firstly, I guess, Heshaam, first question is, where can I get access to the Open API editor tool that was shown there in the demos?
Yeah, absolutely. So the Open API tool, you can search for it on the various marketplaces for VS Code, IntelliJ, Eclipse plugins.
Other question, where can I find out more about the F5 vulnerability that was discussed?
Yes, so F5, they have a section on their website, is where they cover kind of known vulnerabilities. And you can also just find more information, just kind of Googling. There's various websites like Hacker News, Eclipsium, that also will kind of talk about that breach as well.
Okay, cool. So in this Spoutable example, I think it was, you talked about an API firewall. Is that a 42 Crunch product? I wasn't quite sure. So again, well, I can answer that one. Yes, it is. It's one of the service capabilities within our API security platform. So Anthony was showcasing the audit, the scan, and the firewall. So audit and scan are effectively our design and CID design time tooling, and then the runtime protection is delivered through our firewall components. So the platform offers a complete suite of those capabilities. Another question is then, does the scan tool only test for SQL injection or other types as well?
So no, so it doesn't actually test directly for SQL injection. The way it really works is it tests if that API rejects those attacks that fall outside of the defined input. And that would include things like SQL injection if you thoroughly define the inputs in the actual Swagger definition.
Okay, cool. Thank you. And those API tests, can they be automated from a pipeline like GitHub? That's another question there.
Absolutely. So these tests can all be automated through your developer pipelines, GitHub Actions, GitLab, Jenkins. So you can basically take the same types of testing and validation and automate that in your pipelines on a commit, push, pull request, etc.
Cool, cool. I think there's a few more open questions there. Just wondering how such firewall will work with endpoints. Can you see that question there, Heshaam?
Yes, so those fields, so it looks like you're passing in some query parameters into the path there. So all of those are defined in the Swagger definition of that API. So basically, when you generate this configuration that's specific to this API, it's pulled from the Swagger. So it has the context of all those path parameters or query parameters that you might have. And so it will know automatically if those fields are expected or not. So William had a question on, can we rely on the API firewall without having the developers correct any issues in the code? So the API firewall, it relies on just the Swagger definition of the API. So the implementation or the code of that API is not relevant, but the Swagger definition is relevant. So the firewall relies on a well-defined Swagger definition, but you also have different levels of blocking modes. So if the Swagger isn't up to where you want it, you can still utilize the firewall and you can change the blocking modes as appropriate, depending on the progress of your Swagger definition.
Great. Okay, thank you. So hopefully now you can see this is the last bit of news here, folks, before we wrap up. The additional learning. So hopefully you can see on screen there, link to the API security newsletter. There's a QR code there you can scan, or there's the URL there. We also have recently launched our developer community, available at that address there. So again, we'd encourage you to jump on there and share any thoughts, inquiries, and we'll be sure to moderate that with you. And then last but not least, all the free tooling that we have available, you can get it at that address. So if you want to get testing with those, you can sign up today and get using the tools. And then last but not least, upcoming events. There's two. Yesterday, in fact, Heshaam was on a webinar with our colleagues over at Microsoft, Harris and team, and there's a recording of that available where they showcase how 42 Crunch complements the Defender for APIs and helps enterprises with their API security testing. So again, lots of real-world practical use cases there. And finally, if any of you folks are going to be at Black Hat next month, we'll be on the Microsoft stand at that number during the week. So please be sure to swing by and say hi to the team. So again, to our presenters, Anthony and Heshaam, thanks guys, and we'll see you all online very soon.